Hi, my name is Ethan, and today we're going to be talking about design for additive manufacturing. Just a couple logistics before we get started. There is a Q&A attached to the webinar, so feel free to ask any questions as they come up. You can go ahead and chat them in. I do have a colleague on the line. He'll be happy to chat answers back to you. And at the end, I'm happy to pick up any questions live that are left over. I can address them for the entire group, or I'll look through and see if there's any questions that I feel that everyone should know. The best view to view the webinar, if you do have this option, is the side-by-side mode. I do have quite a few metal parts with me here today that I'll be showing off throughout the webinar. If you do have that option, that's the best way to see all the cool stuff that I have with me here today. Let's go ahead and get started. Today we're going to be talking about design for additive manufacturing, specifically about the desktop metal products. Little agenda, we're going to talk really about the design freedom that's available with additive manufacturing, all the cool, awesome features that are now possible to you because you chose to make your parts with additive manufacturing. We'll look at some of the design rules associated with desktop metal products, some of the best practices, and talk about, like I said, best practices. Just a little bit about DM before we get started. Desktop Metal was founded in 2015 with the goal to make metal 3D printing accessible for engineers and manufacturers. And what I want you to take away from this mission statement is this idea of accessibility. These products are very easy to use. They're very affordable. They don't have a lot of operator burden. You know, metal 3D printing has been around for a while with powder bed fusion, but it's really been inaccessible. So Desktop Metal was founded with the idea of accessibility. And I think, you know, if you look at a lot of our customers, look at a lot of our parts, you really see that value proposition shine through, where people really value these products because they're just so accessible. Just looking at some of our customers, you know, adding to this point of accessibility, you know, we have customers that are some of the largest international companies in the world, like the Toyotas and the Googles of the world. And then we have the small 1 or 2 man manufacturers, the mom and pop machine shops, the small design agencies. You know, these systems are really adding value everywhere. So we're seeing it being used across the board from the largest companies in the world to some of the smallest companies in the world. We're shipping in over 49 countries today. So wherever you're watching this from today, we have partners there who are happy to help you, happy to assist you if you want to learn more about desktop metal products or you want to see them in person. You know, important to know we're shipping all around the world. So, you know, feel free to reach out to any of our partners and they're always happy to help you. We have 3 metal 3D printing systems today. The Studio system, which is the printer that I have behind me here today. That's really for our office-friendly production of, you know, prototypes, one-off parts, tooling. It's great for those jigs and fixtures, molds. It's, you know, very, very, very accessible, very, very, very easy to use. And we have our shop system and our production system. Those are both binder jetting machines. Those are for when you want to go from, you know, 10, 15, 20 parts a week to hundreds or thousands, even thousands of parts per day even. Those systems really, you know, really increase the volume and are great for those mass production, high throughput applications. Today, we're mostly going to be focusing on the Studio system, but it's important to know that, you know, all of these applications, all of these printers have the same benefits of additive manufacturing. You know, they have the same freedom available to them, design freedom available to them because of the additive nature of printing. So, you know, we're working across a broad range of applications, you know, just try to get your mind thinking about some of the parts that are being so successful with our products. You know, automotive, things from piston heads, connecting rod, you know, even engine components, gear shifters that can be customized now. Maybe some shock absorber pistons that, you know, have been produced for a long time, but now with additive manufacturing, we're able to, you know, generate some new designs that weren't possible before. Of the thermostat housings, those are from our vintage Mercedes-Benz, where the tooling and you could just no longer get those parts anymore. So what did we do? We scanned them and we printed them. You know, some gearing assemblies, some water pumps, engine mounts, you know, that feature some generative design. Just trying to get your mind thinking about, you know, what are some of the applications we're seeing today on these desktop metal products. Consumer products, things like, you know, golf clubs, faucets, you know, guitar tailpieces, you know, decorative handles that can be very, very customized now because we're printing without the need for tooling. You know, custom skateboard trucks that feature this generative design to be very, very, very light. And then jewelry, of course. If you can imagine all the different tooling that's required for different jewelry designs, different ring sizes. You know, now we can print all those different designs, be very customer to what the end user wants, all without the need for any tooling, making it very, very, very easy and accessible. Machine design. Machine design is a very common industry for us. You know, complex gearing, things that are moving in relation to one another. You know, planetary gear sets that we'll look at and talk about later. You know, roller screws for actuators, gearing, you know, housings, different motor housings, different motor mounts to hold different size motors. All great applications for the desktop metal products because they're relatively complex and, you know, they're usually produced in relatively low volume. You know, looking at heavy industry, you know, has lots and lots and lots of very expensive complex parts that are almost always produced in low volume because they're making one or two of these machines. You know, they're servicing 100 oil wells. You know, so they can justify printing these parts because they're almost always able to greatly reduce the cost and reduce the manufacturing lead time. Think like large gears for earth drilling machines, custom manifolds for chemical processing, you know, a variety of different impellers for different pumping scenarios, you know, different nozzles for chemical processing, you know, different housings, you know, heat exchangers, you know, and then things like fuel atomizers for oil and gas industry. We'll talk about this part quite a bit later. You know, manufacturing jigs and fixtures is a great application for us. You know, there's so many different fixturing and jigs that are required during the manufacturing process. They're all relatively complex. They all require metal, but they're almost always produced in low volume, making them excellent applications for the studio system. Things like drill alignment jigs, you know, end effectors for holding different forgings. You know, very, very small end effectors like you're seeing on the screen, different work holding fixtures, you know, things for the QA processes like the thread checking fixture or assembly fixtures like the smartphone fixture, all great applications for the desktop metal machines. Then there's the actual tooling that you can create. Things like mold inserts that are going to be experiencing very high heat during the molding process. You know, zinc die casting, you know, zinc die casting, you know, more mold inserts for, you know, for actual, the zinc die casting operation on a zipper. We'll talk about that part later. You know, coining fixtures, extrusion die, sheet metal tooling, all excellent applications for the desktop metal machines because again, you know, these are all tools that are relatively complex, very expensive, but almost always produced in low volume, making them excellent parts to print. We're working in a variety of different materials, and the goal here, again, was accessibility, targeting materials that engineers are already familiar with and used to working with. So that way, you know, it's not like some other industries where you're working with these strange alloys that you've never heard of that were made custom for this process. These are all materials that, you know, everyday engineers are already working with and familiar with working with. 17-4 stainless steel, excellent material for its excellent mechanical properties and relatively good corrosion properties. 316L, another common stainless steel. It's a little bit better at high temperatures and in some corrosion environments. Alloy 625, also known as Inconel, excellent at very high temperatures in some specific corrosion environments. H13, very common tool steel, has excellent hot hardness values, makes it excellent for, you know, hot work and cold working applications. It also is great for high temperature cycling. So, you know, an injection mold core that's being constantly heated and cooled, H13 is an excellent material for that. 4140 also has excellent hardness value, common material for end effectors, sheet metal tooling, even, you know, housings and other common low alloy steel. And then of course, copper for those electrical and thermal conductivity applications that, you know, some complex heat exchangers and things of that nature that we'll look at later. So let's start by talking about design freedom. You know, with additive manufacturing, of course, we're producing in an additive nature. We're building parts layer by layer, and this allows us a lot of, you know, design freedom and a lot of possibilities that just aren't possible with other manufacturing methods. Starting with just complex geometries. You know, for example, this is a generative design skateboard truck. This, you know, is a part that was produced via generative design, so we allowed the software to choose where it puts material and where it takes away material. This gives us an optimized design for our loading scenarios, but it's often, you know, it generates a part that's very, very difficult to make. But it's not that hard to print generally. You know, we can, since we're printing this part layer by layer, it's no problem to have this internal webbing features, these complex internal features that would be, you know, impossible to machine or cast, very, very easy for us to print. You know, another part here, I'm actually going to switch over to my overhead camera here to show you some of these parts in a little bit more detail. But, you know, you can see I have this nozzle here that's used in the food processing industry. You know, it features very organic shapes, features some organic curvature that would be very difficult and very expensive to manufacture, but very easy for us just to print. Another part that I have in here too is this assembly line screwdriver tool that you're seeing in the machine. You know, I have the housing piece here, but this features some very, very, very complex geometries and actually quite a few different printed components. You know, all these parts are working together. This is used for actually screwing parts in and out of a fixture in a metal injection molding environment for post-processing. But this, you know, the very, very complex nature of this housing would make it very, very difficult and expensive to machine, but very, very easy for us to print since we're just printing this part layer by layer. These curves and internal features are no problem. You know, on this part, actually, this company, Alpha Precision Group, was able to save 93% cost savings and 87% lead time savings on this part. So right away, you know, a great example of a part to print. Mechanical coupling. You know, this is a mechanical coupling for transferring power between two rotating components. You know, when you need a custom one of these, they're often very expensive and very difficult to manufacture. But we can see here, all these fine details are no problem. We're getting these fine details at not a lot of added cost to the part, which allows us to, you know, create a coupling that's perfect for our application. It's meshing perfectly. It's the perfect design to transfer power. Shaker hook. So I'll talk a little bit more in detail about this part, but this is this shaker hook is used for harvesting nuts and olives. One of these shaker hooks can collect over 3,000 kilograms of olives per day with a falling rate of 95%. So that means it's getting 95% of the fruit or olives off of the tree without damaging the tree or any of its buds. I don't know about you, but 3,000 kilograms of olives is probably more olives than I'll eat in my entire lifetime. So it's a pretty incredible component. It's a very key component, and the design is very important for its, you know, performance, reliability, and usability. You know, so they wanted to generate a new one of these shaker hooks for some specific applications where they wanted to optimize the design for some specific customers for some specific applications. They were originally building that part via an aluminum chill casting operation, which of course is not a very friendly application or manufacturing method for low volumes. So they looked to, you know, they moved to printing, and they decided since they're now going to be making the part out of steel, since they're going to be printing it, they wanted to use some generative design software to really optimize the design. You can see they loaded it into a generative design software. They added some loading. They added that cyclical loading of the, you know, the 3,000 or the frequency that it's moving back and forth, and they let the software decide where it does and doesn't put material. You know, of course, generative design, you know, it produces some geometries that are, you know, impossible for the standard casting, very, very difficult to machine, yet are very suitable for 3D printing. So you can see, you know, here are the shaker hooks after they've been sintered. They look awesome. They ended up being lighter than the aluminum components, the original aluminum components, but just as strong because we're using steel now. And then you can see them, you know, ready for field testing. You can see it actually shaking here. So you can imagine, you know, your nuts and olives are on that branch and they're coming flying down off the tree. So just another great example of that really, really complex geometry that's now available because of, you know, 3D printing. Another great project. This is a project that Turner Motorsports did where they were looking to marry a 2001 BMW M3, which is considered a classic sports car, one of the best handling cars of all time, with a modern V8 engine. As you can imagine, as they started to do this, many of the parts didn't fit. So they decided, you know, one of these parts was the engine mount. They scanned the engine mount, they loaded it into a generative design software, Live Parts, and they let Live Parts decide where to put and where not to put material. The blue planes that you're seeing here are what we call keep out zones. Those are areas where the software is being told, do not put material here. And in this situation, those are parts of the engine where, you know, if you put material there, it would be interfering with the engine. They let the part grow, and very quickly they're able to, you know, generate this design. I have the bottom piece with me here today. You know, you can see the organic curvatures of here, the very organic shapes of this part. And you can see the final parts here. I'll pull this up to the camera. It's a little bit too big to fit in my overhead scope, but you can see that natural webbing, the very, you know, the very organic shape of this feature that would be extremely expensive and very difficult to machine, yet it's no problem just to print these components. This part was actually too big to fit on the volume of the studio system, so it was printed in two components, the base plate that I have here, and then the top plate, and then simply just welded together. Just another example of, you know, these parts, when they come out of the furnace, fully compatible with mass finishing methods or traditional finishing or secondary operations. So things like welding, no problem. Just simply welded this to the top plate and we're ready to go. You can see it actually in the engine here, holding the engine in place. As you can imagine, that engine is very heavy. It's a V8 BMW engine. So, you know, we needed these nice steel engine mounts to hold that thing in place while this car is, you know, ripping down the road. Assembly consolidation. You know, so many parts today are designed for their manufacturing method and not so much for their specific application. So, you know, an assembly may be 20 components simply because it's easier to make that assembly out of 20 components and assemble it with, you know, rivets and fasteners and screws and even welding or even things like Loctite and glue than it would be to make that part all together with traditional manufacturing methods. But with 3D printing, it's very easy and it's very possible to simply print that part all as one, you know, consolidated assembly. Here we're looking at a roller screw. This is part of a linear actuator. It's used to open and close pilot valves in a steam power plant. This part was traditionally manufactured out of 7 components, but they went to go print this part on the Desktop Metal Studio system, able to redesign this part to simply just be one component, greatly reducing the number of parts, reducing the cost from $86 down to $86 per part. Traditionally, this part was costing $1,900. So a huge savings here in cost, as well as the ability to, consolidate that assembly from the original design that was 7 components, with set screws, as well as some Loctite operations, down to just one 3D printed part. Another example of this. This is a crankshaft gear. This gear is attached to the crankshaft on a motorcycle. In a motorcycle engine, it attaches the crankshaft to drive both the water pump and the oil pump. So it has 2 different gears that are, attached to different gears that are then driving those 2 pumps. This part was originally manufactured out of 2 separate gears and then welded together. It wasn't a great candidate for casting all as one component due to some of the difficult internal geometry and the keyways. 3D printing allowed for this part to be easily prototyped with a studio system, and now they're looking to move to mass production on the shop and production system, where they found a design that they like, they validated it off the studio system. Since they're working in low volume, they're prototyping those parts, and now when they want to go to mass production, they're looking to move to binder jetting and move to higher volumes. Another great example of just, even though it's just 2 to 1, it's still a huge cost savings and time savings by consolidating that assembly. Another part here, this is a water wheel. It's part of a BMW car. It's used for driving water for coolant. This part was traditionally manufactured out of an assembly of different plastic components. Utilizing DMOS, which is a powder bed fusion process, BMW was able to re-engineer this part to maximize the performance as one single metal component. However, it was far too expensive and far too slow to produce this in high quantities. It was over $100 per part, and would take a few days per part. So they could really only put this part into their very, very, very high-end racing cars where they could justify that high cost. Moving to the production system, they already have done this assembly consolidation, and now they're able to tweak the design slightly for binder jetting and produce this part at just $5 per part, produce a few hundred of these per day. So now, on the production system, we can move very, very quickly with this assembly consolidation and produce this awesome part. Let's talk a little bit about mass production without tooling. We talk about this a lot, but the ability to be able to produce parts in high quantities without tooling is a huge benefit of 3D printing. For example, look at all of these different geometries. I can print all of these different geometries. I have a few of them here with me today, in high volumes on the shop system without any tooling involved. So let me flip my camera again over to my scope here. I'm gonna find where it is. But you can see, some of the fine details of this component. This would require, some extensive tooling to be involved, quite a complex manufacturing process. But now all I have to do is, upload however many of these I want. I think I can do 200 of these per build on the shop system. I can upload them onto the printer, and the next day I'm ready to, put them into the furnace. Very, very, very easy process. And something that we talk about a lot is the ability to mitigate risk. Since I'm not investing in tooling, if tomorrow I get my first parts out of the furnace and I decide I want to change this part, all I have to do is go in my favorite CAD software, modify the design, re-upload it to the printer, and in a few days I have new parts, compared to having to reinvest in tooling, try to change tooling, which can be extremely expensive. So, being able to 3D print on the manufacturing floor without the need for tooling is a huge advantage of 3D printing. Just some more examples of some more geometries. We'll look at some of these in a little more detail later, but tons of different parts that we've been able to print on the shop and production system, all without the need for tooling. Just looking at a couple different scenarios. These are all different shop build volumes, but these are kind of the 3 main scenarios we're seeing in mass production. We're seeing this, sort of mixed volume production. You can see on the bottom left here, all these different parts are being produced together, all in one build volume. You could imagine asking your machinist or a traditional manufacturing shop to produce you all of these parts. They would have to invest in all different types of tooling, lots of different fixturing. They'd have to write lots of different CNC code to produce all these different parts. Versus at Desktop Metal, we could set up that entire build in just 1 to 2 hours. It'll print overnight. Greatly simplifying the process, allowing you to do this mass production without tooling. Then you can do, batch production of units of tens if you need to get more volume of a specific part, or even up to hundreds of thousands of parts per day of the same part if you really need to move into some of those higher volumes. Just some more examples of, lots of different shop parts that we have here in the office that, we're printing. This printer is really high volume, so there's parts everywhere around the office because it's really just churning out parts. Hard to machine materials. So, some materials, while they're very beneficial for some of their material properties, are very difficult to machine. So things like Inconel. Inconel 625, it's an excellent, or alloy 625, it's an excellent material for its, high temperature resistance, some of its specific thermal properties, its corrosion resistance, but it's very, very difficult to machine, leading to very slow cutting rates, high tool wear, very slow feed rates. This makes, machining this material very expensive. But now, since we're printing on the studio system, there is no cutting. All we have to do is, throw this, this model onto the printer, it'll print overnight, and, we're ready to go. A couple of days, we're ready to, install this manifold into its application. It doesn't really care what material it's printing, it's gonna print at the same speed. Another part here, this valve body that I have with me here today. Another part, this is a valve that's used for different corrosive fluids, so it needs to be made out of Inconel. Would have been very, very, very expensive to machine this, especially with some of the deeper internal channels that this part features, but it's no problem just to throw this on the printer. Another example here, extrusion honing. This is an extrusion die used for, the popular 80-20 profile, as you can see here. But, this part was produced out of H13 tool steel. But then afterwards, all we had to do was a little bit of extrusion honing on the inner face, just to get that critical surface finish that's needed for some applications. Just an example of, being able to post-process the same way you would for many applications, the same way on our printed parts. Zipper mold inserts, more parts that are produced out of H13. I have, one of them here with me today. I'll actually flip back over to my overhead camera. I'm going to be flipping back and forth. I want to make sure everyone has the best view possible. But you can see here, this is a zipper mold insert. This is actually used for zinc die casting operations of zippers produced in H13. This company is Corporation Ray. They get lots of requests to produce zippers in low volume, which generally they can't justify doing because of the high cost of creating these inserts and creating these molds. With the studio system, they're able to greatly reduce the cost of these parts as well as the lead time of these parts, allowing them to actually produce zippers in lower volume. Each one of these inserts can be produced for just $15 in about 4 days, versus the CNC operations, which costing them about $120, taking about 2 weeks. You can see some examples of some, die cast zippers on the bottom here that were die cast actually with these inserts that you're seeing right here. So another great example of, some of that hard to machine material, but, now we can drastically reduce the cost because we're printing it. And then just another example here, a lot of our customers are so happy when all they have to do is machine 1 millimeter or 0.5 millimeter off of a part for a critical dimension or a critical surface, compared to having to machine, an entire, part like this out of a block of a hard to machine material. Their machinists are very happy when they bring them, something like this and say, oh, I just need you to machine, the outer diameter to ensure it's 5 millimeters wide, rather than having to, machine this entire big block of hard to machine material. Another example, just some sinker EDM operations on the top of a mold face, just to ensure that that actual molding surface is achieving that critical surface finish that we need for molding. Another great part. This is a part used for, blacksmithing operation. Another part made out of H13 because it's getting very, very, very hot and then experiencing high loading as it's actually pressing. Many different marks are required depending on, what the part they're building is and who they're building it for. They want to mark it with initials or different part numbers. So being able to print these in H13, they then get it very, very hot and, and tap it into the steel. Very, very, very cool application. Perfect for H13, where H13 loves to get hot and it loves to, has very excellent mechanical properties at high temperatures. Fine features. Printing fine features is something that is very, very, very possible on the studio system. For example, I have this end effector here that you're looking at on screen. This features some very fine features. These end effectors are actually used for installing an O-ring on a hydraulic fitting. They only needed a few of these, right? Because they only have one manufacturing line that's doing this operation. They needed just one of these, 3 of these little end effectors. They can throw all of these on a print bed together, print them overnight, and then in a few days, they're ready to install these onto the actual end effector that you're seeing here. I'll try to zoom all the way in just so you can see just how small, some of these features are. but it would be very, very difficult and expensive to machine, but very, very easy for us just to simply print them. Another example, this is an eyeglass hinge for that was produced on the production system, and this actually features two different parts that were printed together. You know, very, very, very fine features, smaller than a quarter, but very easy for us just to simply print these all as one piece. So we're, you know, doing assembly consolidation as well, compared to, you know, having to produce these as two pieces, assemble them, which would still be very difficult with traditional manufacturing. Just another example of some of the, you know, the tiny little features that we're able to print. This is printed with the high resolution nozzle on the studio system, but you can just see this is a little manifold featuring some excellent resolution. Texting, knurls, and embossing. So this is very common, you know, for sheet metal tooling. So, you know, 3D printing allows you to greatly shorten the lead time and rapid iteration and refinement on sheet metal tooling. So many sheet metal parts are made out of, you know, traditional tooling where, you know, we're buying off the shelf tools and we're just, you know, designers are conforming to those tools. But every now and then you do need a custom tool for a custom job, or, you know, something that will just make your life a little easier. So printing this tooling is something that we're seeing a lot of people doing, especially at a material like a 4140 that has that high hardness value. But, you know, we're able to incorporate embossing, texturing, things that are very common for, you know, feet on sheet metal parts, on cabinets and things like that, as well as logos and embossing like, you know, the D that you're seeing on the screen here. Non-circular holes. You know, with 3D printing, you know, we're so trained in our mind to think about holes being circular. We're used to, you know, taking a drill, we're drilling a hole in the wall, or, you know, we have a drill press, we're drilling circular holes because we have drill bits. But now we're not refined to traditional manufacturing constraints. We're printing this part layer by layer. Our holes can look however we want them to. So a good example of this is this atomizer that I have here. This is actually an atomizer that's used on a liquid natural gas tanker. It mixes steam and fuel in a propulsion system. This part had to be redesigned from a very simple design that did have circular holes to increase the performance. You can see, you know, the company here is John Zink. They very quickly realized that by using a non-circular hole, they were going to be able to increase the performance of this part. You can see the hole they decided to go with in the end is this hexagon, or sorry, not hexagon, is this teardrop shape that you're seeing. This allowed them to actually get the best mixing of steam and fuel that they could find and actually greatly increase the performance of this hole. And you can see they worked with, you know, a variety of different hole shapes when they were iterating on this part to try to decide on which was the best one. Just another example of, you know, additive manufacturing. We're not constrained to circular holes. We can use whatever size hole, whatever shape hole we want. Complex internal features. This is a heat exchanger. It incorporates a conformal cooling channel that we'll talk about in a little bit, but it also incorporates these internal fins. These fins are going to greatly increase the heat transfer rate on this part because we're increasing the surface area, allowing more of this part to be exposed to the atmosphere to be able to transfer heat away from the part. These are features that are kind of on this part nice to have. You know, if this part would have been machined, we wouldn't have been able to justify including these features because they would have greatly increased the cost of this part. But, you know, here we're able simply just to print them, especially the internal ones that would have been very difficult to get a tool in there. We just print those parts layer by layer, including those, including those fins to greatly increase the heat transfer on that part. You know, talking a little bit more about this part, of course, it's printed in copper to allow for that excellent thermal conductivity. We'll talk about the cooling channel later, but this part was printed in copper, cost about $443, which was still an 80% savings compared to the traditional manufacturing method that would have actually not even have included the internal channel that we'll talk about soon. This is used for cooling fluids in a chemical processing operation. This is a sensor holder. This part is used to hold multiple different sensors in a precision location on a running machine. It's taking different measurements. It's very small features, making it an ideal part for the shop system. And printing this part, they're actually able to reduce both the cost and the manufacturing lead time. It also gave them this, manufacturing flexibility. When the design needed to be modified, if they wanted to incorporate different sensors, they wanted to change some of the dimensions, all they had to do was revise the file and send it to the printer. You can see some of the little features, some of the internal features on this part, those made it very difficult for traditional manufacturing, but again, very easy to print. Each one of these parts costs about $7.80, and we can do about 186 of them per build, so about 1,500 of these parts per week. So just an example of the shop system really cranking up the production volume. Internal channels, so we'll get back to that heat exchanger at some point, but The part I have here, this is a mold insert that's used for molding the mouthpiece on an asthma inhaler, as you're seeing here. This part features a channel that's snaking through the part as a conformal cooling channel to help cool this mold during the molding process. This part was printed to near net shape, and then just a little bit of machining had to be done just on the molding surfaces. But since it was printed in H13, again, machining just a little bit of the part is much, much easier and more affordable than having to machine this entire part out of a hard to machine material. During the injection molding process, cooling can account for up to 95% of the cycle time. So by incorporating these conformal coolings, we're able to greatly reduce the cycle time by almost 40%, which is going to allow for more throughput. The company can turn over their injection molding presses faster to new parts, which is a great advantage for them. The high temperatures and pressures of injection molding are perfect for H13, so this was a great part for the studio system because, again, it's going to be produced in low volume. The material here, H13, it cost about $160 on the studio system. The traditional cost was $933, and that's without that internal cooling channel. So just another great example of the studio system. Here's that heat exchanger again. Now you're getting a good visual of the internals here, where you can see that helical channel that's kind of snaking through the part. They're going to be running a coolant through there to even more increase the heat transfer rate of this part. Of course, that channel is impossible to manufacture with any method besides additive manufacturing. But we're able to include that channel in there, print this part layer by layer like you're seeing here, and we're able to incorporate that channel to create a very, very high performance part. You can see it printing up here, and then you can see the finalized part there on the right. Gears. Gears are a very common mechanical component. They're used in tons of different assemblies, but custom gearing is often very, very expensive and very, very prohibitive. Generally you can't justify using a custom gear just because it's going to cost you too much when there's so many off-the-shelf operations. Yet there is still quite a lot of people who do benefit from custom gearing. 3D printing can often allow for the efficient production of these custom complex gearing. They can even, print entire assemblies of gears, in place like this sort of gear set that I have with me here today. I'll talk about that part a little later. But, one of these parts that we're looking at here, some herringbone gears. These parts have sort of a double helix feature to them that are allowing to minimize side thrust while ensuring there's proper alignment. They can't be cut with simple hobbing machines because of that mechanism, but printing them, eliminates that difficult manufacturing method, allows for them to be printed very, very easily, allowing designers to be able to justify using these parts. Pretty cool components, if you ask me. Cool. We'll keep moving. Another example. This is an entire the entire transmission for a power drill, printed on the shop system without the need for any tooling. So you can see the ring gears, the internal gears, the planet gears, all printed. They can all be printed at the same time without the need for any tooling. This means if we want to make adjustments to our transmission, it's no problem. All we have to do is make some adjustments to our file, send them back to the printer, and in a couple of days, we're ready to test out that geometry. We can then move to even higher volumes and produce these parts to actually be end-use components. Moving assemblies. Since we're printing parts in place, we're now able to actually print some moving assemblies. So, I have a hinge here. This was printed on the shop system or the studio system, the printer that I have behind me. But you can see, this is a moving hinge. This was all printed together, yet it's two pieces. But this is impossible to disassemble. This will always be one. This will always be, one part because of this living hinge that we are able to print into place here. Another example of that. Here's a planetary gear set. This entire part was printed all together as just one component, even though, it features planets, features a sun, but, all of this is printed together. I don't know how well it turning will come across on the video, but this is a really fun one to play with and has a lot of great applications. Anywhere a planetary gear set can be used, now we can greatly simplify the manufacturing and design to incorporate it all as just one part. All right, keep moving. Another example, chainmail. So just a really cool example of, this is, 10, 20, 30, hundreds of different parts all being linked together without the need for, separating those parts in assembly, making it very, very simple. And you can think of, tons of different applications that make use of living hinges and live hinges. And then that eyeglass hinge that we looked at earlier, another great example of, print in place assembly, allowing for greatly simplifying the design. This is a bracelet. You know, features 20, 30 different components all printed together that it can never be disassembled. You know, it's a very, very, very cool piece of jewelry. It can be customized for different sizes, different end users. You know, for the very high end, they can choose different shapes, different patterns to allow them to have the exact piece of jewelry that they want, all printed in place together as one component. A true density mass distribution. This one isn't as obvious to the eye, but it's a very, very important one. Since we're able to print parts that have infill within them that are not fully solid, we can decide how dense our parts are. So if we want a part that's maybe a little bit lighter, we can sacrifice some shell and some infill to get a lighter part. Or if we need something a little denser, we can make our part incredibly dense, like I have here, where the infill almost takes up the entire part. We can also adjust that shell thickness to give ourselves different feels on the parts, different designs on the part. One of the big applications we've seen for this is golf clubs. So different size clubs have tons of different variables to them, where they want to be able to fine tune the mass for different players, different styles, different club styles, and then they also want to be able to produce them in low volume for custom end users and custom players who are willing to pay for their own customized things like putters and stuff like that. So you can see here, a great example of a putter. We're able to tune the mass quite a bit by incorporating some of these honeycomb features that you're seeing on this part, as well as on actual irons that you're seeing here, be able to incorporate some infill into this part to help us decide on the exact mass of this component. And then you can see just a couple of different ways for doing this, but it's kind of an awesome feature that a lot of people don't think about, is the ability to really tune our mass to get the strength and the weight that we need. All right, so I hope I've inspired you a little bit and shown you a bunch of different, geometry designs that are possible, a ton of different design freedom that's possible. But now let's talk a little bit about some of the design rules, some of the stuff that you should be thinking about when you're designing for the studio system that I have with me here today, just to help you ensure your parts are going to be successful. So a little bit about the studio system first. Studio system is our office-friendly metal 3D printer. 3 pieces of equipment. It's got the printer, the debinder, and the furnace. It's really the world's first office-friendly metal 3D printing, targeting accessibility. It's great for low-volume applications, functional prototyping, jigs and fixtures, rapid tooling. It's totally safe for the office. It has these several support processes that we'll talk about later. Automated workflow. The entire process is controlled by our software. All you have to do is upload your CAD file, and it's going to tell each of the 3 pieces of equipment exactly what to do. Easy to change materials, familiar materials, shipping in 48 countries. Very, very accessible, very easy to use machine. A little bit about how the 3 pieces of equipment work. You have your printer. It's printing rods layer by layer. Those rods are consisting of a metal powder and 2 binders, a primary binder and a secondary binder. And what the result of that process is what we call a green part. A green part is just being held together by those binder materials. It's still pretty fragile. If you dropped it, it would break. But it's that combination of metal powder and binders. In the debinder, it's that solvent wash. It's going to remove that primary binder from the green part, and we're going to result in what we call a brown part. So it still has the secondary binder in there to hold the part together, but we've removed most of the binder out of that part. In the furnace, we're going to evaporate all of that secondary binder, leaving no binder left behind in the part. We're going to sinter our part to a strong, dense metal part like you're seeing here. Diffusion is going to happen, and our metal particles are actually going to bond together and resulting in a dense metal part. So, what is the result here? We commonly refer our parts to near net shape, and we're getting the resolution, accuracy, and surface finish of, a high quality casting. I have that housing that you're looking at on the screen right here with me. This is a 4140 part. We're getting dimensional capabilities of about plus or minus 0.8%, but it's important to know, these parts, when they're coming out of the furnace, behave very similarly to any metal component. So for example, on this gear here, I printed this part, debound this part, sintered this part, but I needed a critical dimension on the inner diameter. So what did I do? I threw it onto a lathe. I turned down just the last 0.5 millimeter of my inner diameter here to get that critical dimension, and now I'm ready to install it, into my application. That's much easier than trying to machine this entire gear out of a wrought 17.4 material. Another thing, these parts are fully compatible with traditional finishing operations, matte finishing. So things like tumbling, media blasting, plating, welding. This is an example of a part that's been tumbled in abrasive media. That's what's giving it that shiny finish that you're seeing here. So, when these parts come out of the furnace, you can really do whatever you need to them to make them work for your application. So let's start by talking a little bit about supports. Supports work very similarly to how they do in an FDM, FFF part. So same way they would in a plastic application, except for it's important to know that these parts are supporting both the printing process as well as the sintering process. Parts do shrink about 20% in the furnace, and they need to be supported during that shrinking process to ensure that they're not warping and that we're achieving critical dimensions. So you can see here, the purple is our support. It's going to support that part during the entire process, and to ensure that everything is going to shrink at the same rate, our supports are made out of the same material as our part is going to be made out of too. So if our part's made out of 17-4 stainless steel, the support is also going to be made out of 17-4 stainless steel. The raft, which is what you're seeing on the bottom there in blue, that's going to ensure that our part shrinks consistently as well. As your part is dragging across the furnace when it's shrinking on the floor of the retort, or the retort is what's inside of the furnace to hold your parts together, to hold your parts. But there's going to be friction. A raft ensures that all of our parts have uniform sliding friction to ensure we're achieving that better, the better tolerance that we can get out of the furnace. So at this point, you're probably thinking to yourself, wait, why are my supports not just going to sinter to my part, and I'm going to have a support that's just stuck to my part? That's where we're making use of this interface layer that I mentioned earlier. The interface layer is going to be between your support structure and the part to ensure that they don't sinter together. The interface layer is made out of a polymer binder that's used for actually holding the material together, a wax binder that's actually ensuring that the material is flowing during printer, and then a ceramic powder. That ceramic powder has a much higher sintering temperature than the metal sintering temperature does. As the binders are removed out of that, out of that interface layer, it's removing the polymer binder, it's removing the wax binder. All that's left is this ceramic powder. That means that after printing, my support is, I have my support, I have a layer of ceramic powder, and then I have my part. All I have to do is, take my part, I can tap on it with a hammer, I can drop it on the floor, the powder falls out, and I can lift my part right off of its supports. This makes it extremely easy to remove our parts off of supports, and it's something that's pretty unique to metal FDM process like the Studio system. That's, in powder bed fusion, your supports are actually welded to your part, they have to be cut off. So this makes it very, very, very easy, very, very accessible process. We have some great examples on the website of parts being removed from supports if you're interested in seeing more about that. Holes. So we can print holes, of course. Holes can be printed up to 20 millimeters without the need for any supports. The parts can self-support and they'll be fine throughout sintering. When you exceed that 20 millimeters, you're going to need a support. So that's when you have to ask yourself, does this actually need to be a hole? A circle? Can I make it a teardrop? Can I make it a hexagon? Can I make it something that's going to self-support itself? So for example, on the left, the part on the left here, that has a 25 millimeter hole. On the right, I converted that into a teardrop. Now we no longer need that support. We're saving processing time. We're reducing part costs, and now we don't need any support on that part. So it's just something to be thinking about as you're designing your part. Looking at minimum hole sizes, we have two nozzles, the 400 micron nozzle and the 250 micron nozzle. The 400 micron nozzle, the minimum hole size is about 1.5 millimeters. On the 250, it's about 0.75 millimeters. Minimum wall thickness. There is some minimum wall thickness that needs to be ensured just to ensure that your part has enough structure to survive sintering. Sintering does have some stresses induced into your part. As it's shrinking into itself, and that's an opportunity for cracking to happen. You want to make sure you're achieving a minimum wall thickness of about 1 millimeter on the 400 nozzle and a 0.6 millimeters on the 250 micron nozzle. That's going to ensure that your part has adequate structure to ensure it's going to survive sintering. Looking at maximum wall thickness, a part that doesn't have infill. So for example, this part does have infill, of course, as you're seeing. You can see like that hex pattern in there. This does have infill. It's a triangle pattern actually. A part without infill, you can do a cross-sectional thickness of 5 millimeters or up to 10 millimeters across. A part that does have infill, you can do about 4 millimeters thick shell. So just another thing to think about. If you do need a fully dense part, you're a little bit limited, but we're finding that for many applications, having infill doesn't actually affect the performance of the part at all. Looking a little bit more at shell thickness, shell thickness can be easily controlled in Fabricate, which is the software that's controlling the studio system. It can be independently controlled for both the walls, the top, and the bottom surface. Shell thickness grows inward, so if you do want to add some machining stock to your part, if you want to add a little bit of beef, just to ensure that when you're machining, you're not, going to below your minimum tolerance, you're going to want to add that in your CAD software before exporting it into Fabricate to be printed. Then you can increase your wall thickness a little bit, your wall line count, your top layers and your bottom layers. Makes it very, very easy to do this to ensure that you're getting, the exact part that you need with the strength and the weight that you're going to require. Large parts. I have a couple large parts with me here today. Maximum part size is 9.4 inches by 6 by 6, which is a bit smaller than the build volume of the actual printer, because the part's going to shrink by 20%. So your part, the max part size is going to be 20% less than the size of the printer. Though we do recommend trying to stay within a max part size of 6 by 6 by 4.3, just because as parts get larger, they do tend to take longer, they get a little bit more expensive, that it generally can not always make as much sense to print those parts. But it should be known, we print plenty of large parts, and you're welcome to, and many people do print very large parts. Another thing to know, we looked at this a little bit earlier, but parts can be welded. So we're seeing a lot of our customers, they're printing the very, very complex parts of their parts, and then they're welding it to easy to machine components. This is a great way to approach the system, because we're printing the part that would have been very difficult, very expensive to machine. We're getting that very complex geometry, and then we're welding it to some tubing or something that was very easy and inexpensive to machine to kind of have a composite component. Small parts. So the recommended minimum size part on the 400 micron nozzle is about 0.24 inches square. On the 250 nozzle, about 0.14 inches square. You can see, some of the really, really fine details. We looked at this part earlier, but we can print some pretty tiny parts. We do have a minimum part size though, just to ensure that we have a minimum number of top, bottom, and side layers to ensure that this part's going to survive sintering and have enough geometry to it to be at tolerance accurate as well. Aspect ratio. Aspect ratio should not exceed 8:1. For example, if you have a 2mm pin, that should not be any taller than 16 millimeters. Aspect ratios that are higher than that can be at higher risk for slumping. So as it's shrinking, you are at risk of it, maybe leaning, warping, or just slumping in general. So you want to make sure your part is staying within that 8:1 aspect ratio. If you need to exceed that, maybe you need to relook at your orientation, or maybe you need to combine a part or something of that nature to allow you to, get a higher aspect ratio. But, maybe you need to print on its side or something of that nature. Emboss features. Emboss features should be a minimum of, depends on the X and Y. If you're on the 400 micron nozzle, about 0.45 millimeters wide and about 0.5 millimeters high. On the Z, you go about 0.25 millimeters wide and about 0.5 millimeters high. This is just to ensure that you're getting the resolution and to be able to read your emboss. On the 0.25 millimeter nozzle, you can go a bit smaller. In XY, about 0.3 millimeters wide, about 0.3 millimeters high, and in Z, about 0.15 millimeters wide, and about 0.3 millimeters high. If they're too thin, they're not going to print well. You're not going to be able to read it. You're not going to get the resolution you use. So this is just to ensure that you're, to ensure that right away you're being successful with your emboss features. Similarly, your deboss features. Deboss features should be a minimum of, very similar results. On the 400 nozzle, about 0.4 millimeters wide, 0.5 millimeters high, 0.25 millimeters wide in Z, 0.5 millimeters high, or deep, I should say, because we're going in now. The 250 nozzle, 0.3 millimeter width and about a 0.3 millimeter height, 0.15 millimeter width, and about 0.3 millimeter height as well, just for your to be successful with your deboss features. So those are kind of design rules, things that you should be ensuring your parts adhere to. But now let's look at some best practices to help you be successful, to help you design better parts for 3D printing. So radiuses. Radius your edges whenever possible. These features come free with metal 3D printing. They don't add to the cost of your part significantly. They don't increase the print time very significantly, but they can greatly increase the chance of your part success rate. It's going to decrease stress concentrators. It's going to greatly allow the part to be more successful. So when you're designing your part, use your fillet tool liberally. After you're finished designing, ask yourself, can I fillet every single edge that I see here? If you can, do it. It's going to greatly increase the, the risk of cracking of your part, and it's going to greatly increase the, chances of success of your part. Threads. Threads can be printed into the part, or they can be tapped into the part. We recommend that if a thread is less than 10 millimeters, an M10, you should print the hole and tap the thread. If it's greater than an M10, you should print the thread and then chase it with a tap afterwards. Chasing the thread just ensures that your thread's accurate, it's consistent, and it takes no time at all, just to run it through the part real quick. People are always very happy to hear this too, because, tapping, I know I have, tapped, 100 M10 holes in a steel, or an M15 hole in a steel plate. It's not fun. But when they're already printed and all I have to do is chase it, it's a much, much faster operation. Avoid printing fasteners. This is something that, we see a lot of people want to do just because they get their printer right away. They don't know what to do with it right away. So they say, let's throw a screw on it. Fasteners are generally produced in mass quantities at very low cost per part. It's very rare for it to be economical to actually print a fastener rather than buy it. I know here, I'm located in Boston, we can get anything from McMaster in overnight. If I were to place an order today, I'd already have the screw tomorrow morning. So you should actually be thinking about using fasteners to add value to your 3D printed parts instead. Think about where can you be using threaded inserts, set screws, ball points, pins, all these different components that are available to actually add value to your part to create a better part rather than just trying to create these low cost, inexpensive components. Optimize your print orientation. So, obviously when you're going to print your part, you have quite a few different options. So you want to be minimizing your support volume. For example, that part on the right. Don't print with your, where you need supports going very high when you can flip it and have, far less support. That's going to save print time as well as material, and it's going to increase your chance of sintering success because you're greatly reducing forces on the part. Avoid high centers of gravity. High centers of gravity increase the chance of your part toppling during debinding or sintering. It's also going to increase the chance of sintering defects due to high loading on the rest of the part. Also, you're going to want to avoid critical surfaces being in contact with supports. The bottom surface of your part is going to be in contact with that ceramic, which does leave a little bit of a rougher surface finish on that bottom face. So if you have a critical surface, you're gonna wanna put that on top where you're getting the best surface finish. The bottom's still pretty good, but if you do have a critical surface, try to have it not be in contact with supports, try to have it be facing up to get the best, best quality possible. Clearance, this is for different interacting components. It's recommended to add about 0.3 millimeters of added clearance to ensure that the parts are going to interact well. FDM printers, like the Studio System, they tend to over extrude to ensure that you have a better density and better layer adhesion. So this needs to be taken into account when you're designing clearance holes or clearance between parts. So for example, if you want to have a 5 millimeter hole in your part, it's best to print that at 5.3 millimeters. That's going to ensure that after sintering, the dimension is closest to 5 millimeters, just because of that over extrusion process. So use your move face command in your CAD software, create a variable at 0.3 millimeters, and just ensure that all your clearance holes have that added 0.3 millimeters by using your move face command. Avoid overhangs. Overhangs often require large support structures, but generally they aren't necessarily critical for the design. These are going to add to your part cost, your print time, and your sinter weight, which are all things that we're trying to keep low. So use an angle approach to eliminate them, or chamfers and a revolve in CAD. For example, you can see my original design up here requires this large support to support that overhang. In my CAD software, I did a simple revolve to add a revolve feature that's going to add a little build up to that. Now I no longer need a support. So you have a minimum supported overhang angle of 40 degrees from the plane that will require supports. So, very simple to add a revolve, add a chamfer to, greatly reduce that amount of supports needed, reduce your part cost, lower the print time, lower the sinter weight. So just another thing to be thinking about. That's all I have for you here today. I hope you learned something. I hope you're inspired to go out there and try to design some parts for Additive, to get your hands on, some Studio System parts, to design some awesome parts that are making use of those great benefits we talked about earlier. We'd love to set up a meeting with you if you're interested in learning more, if you want to hear, something maybe a bit more specific to your applications. I'm happy to sit down with you. We can talk about, your manufacturing environment, the parts you're working on today. We can look and see if any of the desktop metal products would add value to you. We're happy to, I'm happy to advise on, any parts. If you want to send me an email with your part file, I'm happy to look at that part let you know if I think it'd be a good part for our process. I'll let you know how much that part would cost on our different machines, as well as what the throughput would be, how many you could get per week or per day, or et cetera. If things are looking good, I'm happy to send you a free part sample as well, just to help you with your thought process and whether or not this system makes sense for you. Thanks again. We're going to be doing a lot of these events. Feel free to head over to desktopmetal.com/connect/events. There you can sign up for lots of different webinars. If maybe you want to hear more about material properties or finishing methods, or you want to hear, do a deep dive on how the studio system works. We're going to be doing a lot of these. I'm going to be doing a lot of these. So feel free to head over there, sign up for those. We can chat more. Feel free to email me again. I'm happy to answer any questions, look at any of your parts. Always happy to talk about 3D printing, talk about additive manufacturing. All right. Thanks again, everybody. I really appreciate you taking time out of your day today. Bye.